Hi and welcome to the video lecture series on wear modeling and simulations in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. And this is the third part of the video lecture, which is devoted to abrasive wear. So abrasion. Now this encompasses a lot of different processes: scuffing, scratching, marring, rubbing away, etc. And it can be unavoidable due to normal usage in many ways or due to exposure to natural elements. Some examples of abrasion in terms of two-body abrasion are when we have interacting surfaces in relative motion, one or the other abrades the other, and this is tribology. Pebbles on the beach, they are sliding against each other due to the waves. This is abrasion. And we have abrasive paper, for example, to polish a surface. So that are two-body abrasion. And three-body abrasion is, for example, when we have a fluid with hard particles that is used for polishing, or when we have a wear particle that breaks loose and it abrades one or the other or both surfaces. So in both two-body and three-body abrasive wear, we have these hard protuberances and particles that are forced against and move along a solid surface as they slide relative to each other. And two-body abrasive wear generate straight wear scars, as we can see here on the image that we saw before. Also for adhesive wear, because we have both mechanisms at this type of surface, and the surfaces or the image is again taken from Joel Furustig's PhD thesis. And then on the right we have a three-body abrasive wear example where we can see that although the sliding direction is from south to north, we have some wear scars in somewhat different directions, and these are due to three-body abrasion. Okay, so different causes: two-body hard protruding surface features, so asperity on one or the other surface, or three-body, which is then wear debris or other hard particles coming into the system. And in both cases, these protuberances or debris, they damage the surface through plowing. And there are different types of plowing, and here we see three examples taken from a paper by Scheneler and Bowen from 2013. And we have this first A picture with a purely plastic type of plowing, where the material just sinks in underneath the hard ball and a groove is generated as it slides along the surface. And then we have a plastic, more realistic type of plowing, where we also form this pile up in front of and left, which is then left on the sides of the ball as it slides over the surface. And then we have more of cutting, scraping type of abrasion, where we take loose chips as we plow or scrape through the surface. So as we saw on the previous slide, there were three different types of plowing leading to abrasive wear, but in this course we will model abrasive wear as purely plastic situation with a rigid cone like asperities. So as in the figure below here, we have a cross section of that rigid cone, and it's a hard material, assumed to be a hard material, and we have a soft counter material, and we just plow through that material and generate the bare volume here as in dashed red, as it moves from or moves in time from T0 to 1 delta S over V. And what more is important to consider here is that, okay, this bare volume is very well defined by the height that this rigid cone sinks into the soft material, and of course then coupled to that the cross-sectional area at that height of the cone, which then would be actually proportional to the distance 2a again. And there is also an important angle theta here involved, as we will see. So let's derive now an archer equation for abrasive wear, and we start by considering one pair of colliding asperities. So we let the tip of one asperity sink into the softer material, and under a certain load delta V it will sink in the distance h, and we now assume that or define the width of the cone at h as 2a, and then we just plow this asperity one length, one distance delta s, and it makes this scratch, and the scratch then defines the wear volume. Now, as in the case of adhesion, we again have a force balance equation, Newton's first law, and it's minus delta V plus H times delta A equals 0. So again, we have a proportionality between load, asperity load, and asperity area, which is then asperity width at height h squared, as we see here. So the wear volume can then be formulated through the use of the angle theta. So then we have delta V, the wear of that this small wear caused by sliding this asperity distance delta S is just proportional to a squared times the tangent of theta times delta S. And because of the load balance, we can formulate it as the sliding distance delta S times the tangent theta times the asperity load over the hardness of the softer material. And this means that the total delta V, okay, if there are many of these asperities on the surfaces, so we sum them all up and we get the same type of proportionality as before. So we have capital delta V for the sliding length as per sliding length. Delta S is delta S times tangent theta times the applied load over the hardness H. Again, let us define K abrasive now, subscripted abrasive as the wear rate, and then we have an Archer's law for adhesive wear, and here we've also assumed that if the wear behavior isn't changing during the sliding, then we can express it in terms of the total sliding length S instead of the small sliding distance delta S. So here we see a molecular dynamics simulation of abrasion in which a cone formed tip is plowed into a substrate, and we can see how it breaks loose these particles and it just plows into the surface as it slides relative to it. And you have the reference for the paper down here, down below, if you like to investigate this further. Another simulation of abrasion was made here at Luleå University of Technology by Xiaoye Gang, and here is some images or some figures from his licentiate thesis showing the stresses in megapascals as one asperity slides past the other one, and we have four stages of intermediate time, and we can see as it has passed by at stage 4 we have left two very deformed surfaces with the residual stress field inside, which is quite concentrated with maximum stresses at the contact surfaces.